Hi, Mr. Green here, just here to take you through the next section of the electricity topic for AQA Physics. This covers static electricity and electric fields, and your learning objective is to know the causes and dangers of static electricity and how electric fields can vary. Please pause the video whilst you take that down as you type. Okay, start as we always do with some retrieval practice. So 5 questions there. Please pause the video whilst you answer them and restart when you would like the answers. Okay, so question 1. What's the units of charge? That would be the coulomb. What are the units of potential difference? That would be volts. What's the definition of current? Current is the rate of flow of charge, so how quickly charge flows. What's Ohm's law? Ohm's law can be defined as an equation, and that equation is potential difference equals current times resistance, or V equals IR. And question 5. What's the rule for resistors in series? Total resistance of the circuit is the sum of those individual resistors. Okay, so our learning outcomes today are to state how static charge can build up, to state the effect of statically charged objects, to know the dangers that static electricity can cause, and to draw an electric field and explain how the strength of that field can be varied. Okay, so for our first task today, bit of revision, just label the parts of that atom. So you've got part 1, part 2 and part 3. Please label those, pause the video whilst you do so, restart when you would like the answers. Okay, so number 1 in this case is the electron, number 2 is the nucleus, and number 3 is a proton. Again, the relevance of this will become clear once we start talking about static electricity, because we are talking about the atom itself and the electrons there. So electrostatic charge. Sometimes we get small electric shocks. Sometimes getting out of a car or touching the metal after walking on carpet, you'll get a little tiny electric shock. If you're wearing a jumper, if you take it off, you might hear that crackle, or I'm sure you've rubbed a balloon on your jumper and then made it have your hair stand up. These are all effects of what we call static electricity. We can give lots of insulating materials a charge of static electricity by rubbing them. Again, it's insulating materials that hold a static charge because they can't conduct that electricity, it can't flow away, so they hold on to that charge and become charged up. Sometimes we call it an electrostatic charge. Okay, quick progress check. Pause the video and answer those 4 questions. Restart when you'd like the answers. Okay, question 1. 2 things that static electricity can do. Give small electric shocks, make your jumpers crackle, or make your hair stand up when you've rubbed a balloon on your shirt. What kind of materials can be given a charge? It's insulating materials that will hold on to that static charge. It can't flow away, it hasn't got the free electrons to move that away. Where are these particles in an atom? So where's the proton? It's in the nucleus that's right at the centre of the atom, and the electron orbits that nucleus around the outside. A neutral atom's got 10 protons, so how many electrons does it have? It'd have 10 electrons. And why? For the atom to be neutral, the negatively charged electrons need to balance out the positively charged electrons. 10 positives plus 10 negatives overall equals 0, or neutral. So how do we give materials a static charge? Now, if we rub 2 insulating materials together, electrons might be transferred from one material to the other. We can knock these electrons off these outer shells and they can transfer from one to the other. Protons can't be transferred because they're fixed in the nucleus of the atom. So it's only electrons that can move from one material to the other. If we get an acetate rod, a plastic rod with a piece of cloth, and we rub them together, some of the electrons in the acetate rod will move onto the cloth. That means the acetate has now got more protons than the electrons. It's lost those electrons onto the cloth. So it has a positive charge. There's an unbalance on there. The cloth has got more electrons than protons, so that then gets a negative charge. It's unbalanced in favour of the electrons. So when we rub those together, the electrons moving from one to the other causes them both to become charged and causes them to become oppositely charged. Again, quick progress check. Please pause the video and answer those 3 questions. Make sure you read question 6 properly. Restart the video when you would like the answers. Okay, so question 5a. Which particles can be transferred when you rub an insulating material? It's the electrons that can be transferred. How do we explain that? Protons can't be transferred. They're in the nucleus. They're held in really tightly on there. But the electrons are on the outside of the atom, orbiting it. So with enough force, with enough energy put in there, they can be knocked off. Question 6. Acetate rods become positively charged when rubbed. Explain why a polythene rod gets a negative charge when you rub it. Answer for this one. When a polythene rod is rubbed, electrons move from the cloth to the rod. It's the opposite way round than in the acetate rod. Electrons go from the cloth to the rod. This makes the rod negatively charged and the cloth positively charged. Now when we get charged objects, two objects with a static charge, if we bring those close to each other, they'll exert a force upon each other. If the charges are the same as each other, the two objects repel. So if I bring two statically charged objects together that are negatively charged, they'll repel, they'll push each other away. And the same if I bring together two statically charged objects that are positively charged, they will again repel and push away. If the charges on the objects are different, if they're opposite charges, the two objects would attract each other. So the positively charged object would attract the negatively charged object. Okay, question 7. You rub two balloons on your jumper. Explain why the balloons will then repel each other. Include those words in your answer. Pause the video and attempt that question. Restart when you'd like the answer. Okay, so when we rub the balloons on our jumper, electrons move from the jumper to the balloon. This means the balloons now have more electrons than protons, making them negatively charged. As both balloons are now negatively charged, when brought together they will repel, because objects with the same charge will repel each other. So static can help us describe lightning and explain why lightning occurs. When clouds move around each other and clouds have particles within there, that static electricity can build up between those clouds because of friction. It can cause a spark to form between the cloud and the earth. And we see those sparks as lightning. There's a big potential difference between the clouds themselves and the earth. And so that means charge can build up, and if the potential difference is big enough, then that can then leap to the earth. Lightning is one of the examples of the dangers of static electricity. And buildings can be protected from this by using what's called a lightning conductor. All that is a strip of conducting material, like a piece of metal or rod of metal, down the side of the building. And that lets the lightning travel safely through that rod rather than the building itself. Again, when you're in a car and lightning strikes it, you'll be safe because the electricity carries through the metal body of the car. Lightning happens, as I've said, because there is a large potential difference between the cloud and the earth. Potential difference is a measure of the energy that could be released when the charge moves. The bigger that potential difference, the more energy released. The greater the charge, the higher the potential difference. Now you sometimes build up electrostatic charge by walking on a carpet, and you only know you've been charged when you touch a metal object such as a doorknob. You'll feel a small electric shock when the charge on you flows through that object, and that's the shock that you feel. So charge builds up on your shoes, as your shoes rub on the carpet. Carpet's an insulating material, so the charge can't flow anywhere. There's a potential difference then between you and the metal of the door, so the charge flows through you to the door. Bang, there's your shock. You're then discharged. Don't carry the charge anymore. Static's only dangerous when it's likely to cause a spark. So if a conducting path can be provided to discharge the static, there won't be any spark at all. So people mending computers use an anti-static wrist strap connected to the casing, and that stops any discharges damaging the components which could be destroyed by a spark. Again, when refueling planes, static electricity can build up as fuel flows through a refueling pipe. So the aircraft can also build up static charge as they move through the air. A bonding line is then used to connect the aircraft to the earth before it's refueled. If there's a spark between the aircraft and the fuel line, that's going to ignite the fuel, and it's going to be very, very dangerous. Okay, four quick questions there. Please pause the video and answer those. Okay, question 8a. What causes lightning? Lightning is caused by static building up on clouds, causing a potential difference between the earth and the cloud, and a spark is then discharged. Why is it dangerous? Because it carries lots of energy and it can damage buildings and cause fires. How can buildings be protected against that? You can use a lightning rod. And this works by if lightning is striking the building, the charge travels down the lightning rod to the earth rather than travelling through the building causing damage. Question 11, 12. Can you pause the video and answer those questions? Okay, question 11. People working on electric equipment wear wrist straps that connect them to it because it prevents sparks between them and the equipment, which could damage the equipment. How could a spark cause an accident when an aircraft being refueled? It could ignite the fuel. How does the bonding line prevent this? Charge travels down the bonding line rather than to the fuel. And why is it important that bonding line is connected before the fuel nozzle touches the aircraft? The plane is not discharged until the bonding line is connected. Charge could still travel down the fuel nozzle and cause a fire. Okay, quickly, electric fields. A charged object will create an electric field that we can't see, but it surrounds it. If another charged object is placed into that electric field, a force acts on it, and this is a non-contact force. They don't have to touch for that force to be exerted. Diagrams above show the electric field around charged particles. The arrows show the effect the field would have on a positive charge placed into the field. So near the positive one, it would be pushed away and repel. Near the negative one, it would be attracted to it because it's an opposite charge. The strength of that field depends upon the distance between the objects and the amount of charge they have. The closer the objects are, the stronger the field. The bigger the charge on the objects, the stronger the field. Okay, so our final questions here in our progress check. Draw a diagram showing the field around a positively charged sphere, then a negatively charged sphere. Make sure you include the arrows showing what would happen to a positive particle placed within that field. And question 2, what affects the strength of the electric fields around a charged object? Please pause the video whilst you answer those questions. Okay, question 1 then. A positively charged sphere there's the field around the positively charged sphere. Arrows pointing outwards. If we placed a positive charge anywhere within that field, it would be pushed away. A negatively charged sphere, arrows are in the opposite direction. Shape of the field is the same, but if we placed a positive charge there, it would be attracted to the negative. What affects the strength of the electric field around a charged object? The distance between the charged objects, the closer together they are, the stronger that field is, so the more of a force they will feel. And the amount of charge an object carries, one that's really, really charged up, will have a much stronger electric field than one that's got very, very little charge. Okay, I hope that lesson was useful for you all. There's lots of videos available on our YouTube channel for you to revise and look through. Thank you very much for listening. See you soon. Goodbye.